Good morning again, class. We're going to finish up the last chapter in the review. The last chapter is chapter 3. That's going to be on your midterm. This is a build from chapter 2. These are more properties of derivatives. Okay, so again, remember the number e, and remember it is a number. Okay, so for example, if I have something like f of x e squared, that is a constant. So what is the derivative of f of x to the e squared? That is 0. However, f of x, if f of x is equal to e to the x, then f prime of x is equal to e to the x, and vice versa. Okay, and we'll get to it becomes more complicated when we get to the chain rule. But e is a number, and it's defined by the limits given here. And really, it's like 2.781. Keep going. It's like the number pi. All right, so here are some derivatives. Okay, so if we take the derivative of an exponential function, right? The derivative of b to the x. It is equal to b to the x ln of b. So the key thing is defining b. Okay. Again, there are some properties of logarithms. I would take the time to write them down. It'll help you simplify some of these functions. All right. And so then the derivative of a log function is 1 over the natural log of b times 1 over x. Okay. And so here's a change of base formula. Okay. If you have this, then you can rewrite it like this. I don't think you'll have too many problems like this one, but you will most likely use the derivatives of an exponential and a logarithmic function. That is 3.2. Now here are the natural logs, the derivatives of e to the x. You're going to use this a lot, and you're going to use this a lot. Okay, they're easy to remember. These particular ones that are boxed are much easier to remember. The ones here that are underlined, you're going to need to write them down, and they tend to be a little bit harder to remember. All right, product rule. Okay, if you have this F stands for first function. This second S stands for second function. For example, if you have f of x is equal to 3x times x plus 1. Now you can multiply it all out, or you can just define 3x as your first function and your second function as x plus 1, and then define it as the variable is concerned. And so really you want to find f prime of x, which is just 3, and s prime of x, which is just 1, and then plug it into this formula. The product rule, important. You will use it. Quotient rule. Top, t of x is top. Okay, t of x is top. B of x is bottom. Okay, bottom, right, times the derivative of the top minus, okay, the top times the derivative of the bottom, all divided by the bottom squared. Okay, and another way to remember it is low d high minus high d low all over low squared. Okay, chain rule is a type of substitution. Okay, we're going to look at our basic properties, right? All of our basic property rules are rules for exponentials, and then we're going to make some substitutions and plug them in and make our lives a little bit easier. So the product rule, quotient rule, and the chain rule were a build on the basic properties that we learned in chapter 2. So again, we did a lot of examples last week in class, and so you can look at 3.4 and 3.3 for examples of these types of rules, and you will have them. So again, identifying your function. Chain rule typically focuses on maybe there is a power rule within the chain rule. So for example, f of x is equal to, I don't know, e to the x plus 1 squared, right? And so you determine what your f of x is, and then you solve it just like you would a normal power rule function, but you just multiply it times the derivative of whatever is on the inside. Okay, there are some other special cases, right? Here is a special case, the derivative of a function within a natural log and a function within the base e, right? So notice it's base e, everything stays the same, but again, times the derivative of whatever we consider to be f of x. So the key part in the chain rule is determining f of x. We don't necessarily cover implicit differentiation in the depth, like the definition and all of the ideas, but we do cover it in related rates, right? When we cover differentiation with respect to t, okay? And so you are covering implicit differentiation, but when it comes to related rates, we will not cover the elasticity of demand for sake of time, and it is a sort of complicated topic that we do use derivatives in this idea of demand, and the idea of a demand being elastic and inelastic. I said that backwards, but we are not going to cover 3.7. I'm sorry, I shouldn't put a star. We're not covering 3.7.